Today we're talking about functions and their notation. At the end of today's lesson, we're going to be able to determine if a relation is a function and be able to use function notation to evaluate functions. A function is a relation in which each element of the domain corresponds with exactly one element of the range. Now we should remember that the domain represents all of the x values or input values of the relation, and range represents all of the y values or output values of the relation. Now there are many different ways a relation can be presented to you. We're going to cover all of them. The ones you see here is a mapping diagram in number 1 and a table in number 2. So let's talk about that mapping diagram first. The mapping diagram shows your x or your input values on the left and your output values or y values on the right. Now, in order for it to be a function, every x value should have a unique y value when you trace the lines. So if we just check all of these input values, 3 is going to 2, -2 is going to 1, -1 is going to -1. You follow the arrows. We could rewrite these as coordinate points, x, y, if you really wanted to. However, I think checking from the mapping diagram is easier. I notice that each of these inputs has a unique output. There's no input that has two different outcomes. So I'm going to say, yes, this is a function. Passes the definition. Similar to the mapping diagram, the table does show input, output, input on the left, x values, output on the right. Hopefully you guys are familiar with tables from Algebra 1. It is a common representation of relations and functions. We just want to check that every input is unique and has a unique output. Now looking at this input, I do see that there is a value represented twice. Here we have -1 and -1. So I'm just going to circle those so we can look at both the input output together. If we look at those, that is going to be a coordinate point of -1, 0. Technically, that's just a repetition. That's not a second point. That doesn't violate having two different outputs. This is saying if you put -1 in, you're going to get 0 out. They just happen to list it twice, which is redundant, but doesn't violate anything.
Even though we have this redundancy, we still need to go back and check the full list. If we notice, we have an input of 4 here with an output of 3, and an input of 4 here with an output of 5. So as we were saying, we need a unique output for every input. So 4 has 2 outputs, which makes this not a function.
Now, these are only some of the representations of functions we will be dealing with in class. We are also going to be looking at graphs and, equations. We do have to be comfortable with this definition in all forms. Lucky for us, on a graph, we have something called the vertical line test. The vertical line test states that if a vertical line passes through more than one point on the graph of a relation, then the relation is not a function. We do have to remember that vertical lines run from up to down. Basically, if we can put that point and slide it through the graph, if we slide it and it hits 2 points anywhere, even if it's only one area, it violates the definition and it is not a function. So we want to look at the vertical line test and determine if these relations are functions. We want to take our vertical line. So I'm going to just draw a vertical line for us to look at. If we take this vertical line and slide it anywhere throughout the function, we notice that we are only hitting 1 point. Now, if we look here, it does kind of look like we might be hitting more than 1 point on the very edges of this function, but we do have to remember that as we zoom in, those are going like a little bit out to the side and up at the same time. It just has a steep slope. So this here actually doesn't violate the vertical line test. Anywhere we move this vertical line, it's only crossing through the function once. So number 3 is a function. If we take the same vertical line and move it over to graph number 4, we notice that this relation right away violates that vertical line test. It is crossing through twice here on our vertical line, we have a point where the input of -2 would be up here and the input of -2 would be down here, giving us two different y values. If we write out the points, like this one would be -2, let's say 1.1. This one would be -2, -0.6. Those are the same input with two different outputs. So fail the vertical line test here. No, not a function. You really don't need any evidence. You could just say like not a function fails the vertical line test, and that is totally fine. So when we talk about relations and relations that are functions, we do use function notation. Function notation is something we use in upper level mathematics as a way to abbreviate evaluating functions and just to represent a relation and tell readers about it without using a lot of symbols. So function notation is f of x. It's written like this. It could be any letter. What it says is your input is in the parentheses, in this case, x. Your output is the entire thing, f of x, the whole thing. It's kind of a fancy way of writing y if you want to think about it that way, but it could be any letter. So function notation generally is f of x. We use f of x a lot, but you could see like p of x or m of x. We try and stay away from some like x of x. Technically you could use it, but it gets confusing. So when we read it, we say f of x, just like that. This notation is not multiplication. You cannot divide by f to solve for x. That is not how this works. This notation is saying replace the variable x with whatever's inside in the function f. So it gives you a place to put it. It's a full sentence in like 4 symbols. So easy. So for our examples, we want to use function notation to evaluate functions. These are given functions or known functions. And this notation is saying, let your input be -2 in the function f. Okay, so my function f here is this graph. My input is -2. Well, my input in a graph is generally the x-axis. So this is just a fancy way of saying, let x equal -2. The question is, what's the output? Find f of -2. Find the output when x is equal to -2. Replace x with -2. The first thing I have to do is find where the input of -2 is on my graph. If I look at that, x is equal to -2 right on here. So we're looking at the output there. Well, the output, there are 2 points that has -2. One has an open circle, so it's not included. So that's not actually the value. That won't have an output there. One is closed circle, so that's included. So what I'm actually looking for is the y value of the closed circle. So f of -2 in this case is equal to the y value at this closed circle point right here. The output there is 0. So f of -2 is equal to 0. We're looking for this number here. So f of -2 is equal to 0. 0 is our answer. We have a full sentence here represented. It's saying the function evaluated at x equals -2 is 0. The output is 0. But we didn't have to use that many words to write it, which is nice. We are okay if you just say 0 as your final answer. That's fine too. The important things here is you're not dividing by -2. You're not solving for -2. You're not getting f alone on one side, those kind of things. That is a statement. Those are stuck together. It's a complete sentence, even though it doesn't look like it. So number 6, we have an equation. Our question is saying, what is the output if you replace x with -2? So my first step in this equation is to replace all of the x's with -2. Then we're in order of operations land. So we're considering PEMDAS as we work through this. All of my parentheses, there's really nothing that I can simplify. I do have to remember that technically this is -1 times -2 squared. And that's a small detail that throws a lot of people. So parentheses are simplified. Next is exponents. I have a squared that I need to work with first. -2 squared is +4. So I'm going to write that as a multiplication statement here. That is my only exponent in that problem. Multiplication and division, we work from left and right. I do have -1 times 4, which is -4. And I also have 3 times -2, which is -6. Copy the -1 because I haven't touched it. And then I add, subtract from left to right. So -4 minus 6 is -10, minus 1 is -11. So here, our output is -11. We could say the full sentence, the function f evaluated at -2 is equal to -11. We are okay if you just output the number as long as you're doing it accurately. The main idea with evaluating functions, the takeaway we absolutely need you to have from this lesson is that you replace the variable with whatever's in the parentheses. So in this context, we are replacing x with -2. I need you to have that vocabulary of replacing. Replacing is really going to help us in the future.